Alright, so in this problem, we are going to find the direction of the current in the resistor as shown below at the instant that the switch is closed, after the switch has been closed for several minutes, and at the instant that the switch is opened. I will be answering part A and I'm gonna leave part B and part C to you. Alright, so here is our setup. We have a solenoid. So we have here a solenoid with a battery and a switch. And beside this solenoid is another solenoid that contains a resistor. So we are going to determine, for the first question, we're going to determine the current through the resistor at the instant that the switch is closed. So meaning this switch right here. Alright, so the moment that the switch is closed, so if we're going to close the switch now, current flows through the circuit, or current flows through the wire that is being wrapped around the solenoid. Now remember that current, when we use the right-hand rule, we should be referring to the conventional current, and therefore it should flow from the positive end of the battery towards the negative end. So it should flow from positive to negative. So we would trace that. It flows from, let me just use a different color. It flows from positive to the negative, towards the back of the solenoid, then down in front, down, 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 all the way towards the negative end of the battery. Any questions so far? Any questions?
No,
Alright, I hope this one is clear. It's very important to remember that the current flow should be conventional current. That means that it flows from positive towards the negative. Now, using your right-hand rule, you should be able to determine which side of this solenoid is north and which side is south. So I'm gonna put this as A and B. Now, can anybody tell me which side is north? Pole A or pole B? Use your right-hand rule. That means your fingers should curl down while the thumb points in the direction of the north pole. So in this case, if you refer to this solenoid, which pole is the north? Is it A or B?
Mr. Paul A.
So again, your fingers should curl down in the direction of the current, and then the thumb would stick out where the north pole is. So if you are looking at the screen right now, my thumb would be pointing in this direction. So as I curl my fingers around the solenoid, so the fingers should be now pointing downwards. You curl your fingers downward. Your thumb sticks out towards B. Do we all agree on it?
Yes.
Alright, so once again, as we curl our fingers downward and wrapping it around, so you could just imagine, try grabbing your pen, and the pen becomes the solenoid. So you wrap your fingers around the pen, the thumb points in the direction of the North Pole. So in this case, B is the North Pole of this magnet. And remember that if we have if we have a bar magnet, excuse me, North Pole, South Pole, the magnetic field in the North Pole points in this direction, while the magnetic field on the South Pole points in that direction. Now, this is very important because as you have seen the video on Lenz's law, there are 4 things that you need to answer. The first question is, what is the direction of the existing magnetic field? So in this case, the existing magnetic field is provided to us by the solenoid right here. And to answer that question, the direction of the existing magnetic field to which this solenoid is exposed to is going to be this direction. Because again, this B is the North Pole, so this is the magnetic field on that side. On the other hand, that's on the other end, this is the magnetic field. So as far as the solenoid on the right is concerned, the direction of the magnetic field that this is exposed to is actually directed to the right. So that's the magnetic field that the solenoid on the right is exposed to. That is our number 1. Any questions so far? All right. Now, in relation to the previous state, this is now the magnetic field. Is this magnetic field increasing or decreasing in relation to before the switch was closed? Is this magnetic field increasing or decreasing? Yes?
Increasing.
Why is that so?
It used to be 0. It used to be turned off.
Very
then we
good.
gave it some magnetic field when we connected the switch.
Exactly. This is actually a question similar to what I have asked in the previous slide in class cake. So initially, there was no magnetic field because we did not turn on the switch. The switch was not turned on, and therefore there's no current that flows through the solenoid, and without current there wouldn't be any magnetic field that's created. So going back to my question, this magnetic field has actually increased because initially there was no magnetic field, and then when you turn it on, this magnetic field was created, and therefore there was an increase in this magnetic field. So as a result, according to Lenz's law, the solenoid now will create a magnetic field that opposes the change. And I have mentioned this on the Edpuzzle task, that if this magnetic field is increasing, then therefore this solenoid on the right will have to create a magnetic field that will oppose this increase. So therefore, what is the direction of the magnetic field that the solenoid on the right will create? Anybody?
Left.
Very good. It will create a magnetic field that points to the left. So therefore, the magnetic field of this solenoid will be directed opposite to the direction of the magnetic field that is created by the solenoid on the left. And now, using your right hand rule, the thumb points in the direction of the magnetic field. The curling of your fingers would now be the direction of the current. So with the thumb pointing to the left, you will curl your fingers up around towards the back of the solenoid as you point your thumb towards the left. So therefore, current in this case would be going upward, and then back towards the solenoid, down here, from right towards the left of the resistor. This is right, then left, then up right there. Then we have found the answer to the question number 4. Current would go from right to left of the resistor. Any questions? Any questions, gentlemen?
I don't think so, Mr.
All right. Now let's go
Mr. I
to...
have one question. Is it okay?
Say that again?
I have a small question, Mr.
Yeah, tell me.
Mr. When we use the right-hand rule regarding the solenoid, does it always have to be like curling in the direction of the backside of the solenoid?
No, like for example, in part A, the solenoid on the left. The solenoid on the left, you actually are curling your fingers towards the front side of the solenoid. You have to look into the direction of the current. Is that clear, Majid?
Mr. When I curl my fingers the same way as the left solenoid, I still get a current which is, my thumb is pointing to the right for some reason. When my fingers are facing me and they are pointing downwards.
Your fingers are pointing you, they're pointing downwards. So this is actually the direction of your thumb. The thumb points towards the left side of the left solenoid. I mean right side, sorry. B.
Yeah.
Then that's actually what we have done here. So what's confusing you?
Nothing, Mister. I just realized.
All right. Now, on the other hand, for the solenoid on the right, your thumb would be pointing towards the left. Then automatically your fingers would be curling upward in front of the solenoid and then back and then downward on its back.
I understand that, Mister. I see now.
All right. Any
I was
other
confused about
questions?
something.
Okay, let's look at part B. After the switch has been closed for several minutes, what happens here?
Mister, there won't be a current.
Why is that so?
Because the solenoid on the right is going to oppose it, and after some time, it will burst out, I think.
Burst out?
Balance out.
Balance out. What do you mean by balance out?
Like one side is pointing to the right, and the other is pointing to the left. And after some time, the magnetic flux will be zero. They will balance each other out. They will have an equal.
I see your point, but when will EMF be induced? Or what should happen in order for EMF to be induced according to Faraday's law? There has to be what?
Magnetic flux.
There has to be magnetic flux. There's actually a very important word before that. In order for EMF to be induced, there has to be a change in the magnetic flux. So, in this case, after the switch has been closed for several minutes, you could no longer say that there is an increase or a decrease in the magnetic flux because there's no change in current, there's no change in any other factors, so therefore there wouldn't be any change in magnetic flux, and there's no change in magnetic flux, then there will be no induced EMF. If there's no induced EMF, then there's no induced voltage. And any questions about that? All right, for part C, at the instant that the switch is open, when you open the switch, there will be a change in the magnetic flux because from the point that there was a magnetic field, when you turn off the switch, magnetic field diminishes. So therefore, as a result, the solenoid on the right will have to create a magnetic field that would oppose this change. And that is what I would want to hear in your explanation to parts B and C. Any questions, gentlemen? All right, if none, then make sure that you make a submission to this slide and tap on please check.
I didn't understand part C.
Part C is the exact opposite of part A. So if in part A there is an increase in the magnetic field, in part B, there will be a decrease in the magnetic field because once you open up the switch, the solenoid on the left, the solenoid on the left would no longer have a magnetic field. So initially, there was an existing magnetic field, and when you turn off the switch, this existing magnetic field diminishes. And as a result, the solenoid on the right will have to create a magnetic field that will oppose this decreasing magnetic field. It will have to create its own magnetic field to counteract the change in the magnetic flux. And then you will use your right hand rule to identify the direction of the current that flows through the resistor in part C.
Okay, fine.
All right, so that's the end of my discussion. I'll be putting an explanation to the link of this explanation on this link, but it will take some time as I need to upload it to my YouTube channel. For now, you may work on this task on slide 27.